Hello everyone, this is LemonHX again, and today is the second video of writing algorithm in Haskell. And today I'm going to talk about red-black trees. So here we are, the Wikipedia of red-black tree. And you see, this algorithm is invented in 1972, and the space is on, search is on log n, insert on log n, and delete on log n. So why they invented something like red-black tree, or in other words, balanced tree. So in the extreme situation, your tree will probably look like a line because the first element is the smallest and the last element is the biggest, so it goes to all right. Or the first element is the biggest and the last element is smallest, so it goes to all left. That situation caused the tree as a search tree have something like a search efficiency more or less about a normal linked list like n. So that's not the thing we want to look at. So the red-black tree is a fast implementation of a balance tree, and there have another called AVL, but that's kind of difficult to implement in Haskell, neither a user-friendly implementation. And today I'm going to implement immutable red-black tree. So here we are. And the red-black tree have 4 situations for rotating. So why they call red-black tree? Because depending on the color, they rotate the tree to keep balance. So for example, here. So this, you see 2 red and another red. Because it's 2 red meat, and the tree just detected, and they just change the color of the up part. And here, again. And here, because of the left, and it goes to right, because 1, 2, 3, 4, 5, and you want to keep 1, 2 here, and 3, 4, 5 here. I already wrote some ASCII for explaining that. So let's start coding. So here we are, the last tree we implemented. This is a normal balance tree. And I want to implement a red-black tree now. So first let me see if the linter works. Yeah, it works. So now I want to create because all the balance tree need to rotate. So I need to define a type class for all the rotate balance or rotate behavior. So here we are. This is a balance. So not really. I'm not returning elements. So we have the tree and we return a tree. So actually probably a copy. And then we're starting defining the color because we have red and black. So we define a color of red and black. Deriving a show and an EQ. In this time, why deriving an EQ? Because we probably need to check is that a red or a black. And now we starting defining the red-black tree. So as you see, red-black tree just a normal tree with the color red or black. So it's simply just red-black tree A. We just copy the definition of the binary search tree. So here we are, our node, and we have a color on the node, and then we are just copying the definition of a normal search tree. Okay, now we have the RBT and RBT color for red-black tree and red-black tree color. And the bar tree type class is the balance. So we have 4 situations for balancing the tree. I just pre-write it for them. So this is the first situation. You can see here the hold on, I probably miscopied some part. So here is the thing. So that the first X is for the red node, and the squared X is for the black node, and this is the rest of the tree. You can see the black node goes to the top, and the red, and you have A, B, C, D. And now I need to balance the tree to something like, you can see this tree goes all left, and I balance it to the Y in the middle, of a red, and the X, AB here, you can see this goes to left, and CD goes to the right. Okay. And the second is this situation. Wait, I copied twice, I guess. So here we are. So we can see this, the black on the top. This is a black on the top, and there's a red and another red, but it has a red and the right only have one. So we need to rotate to the Y as the top again, and then the X as the left, because they have A is smaller than B and than C, and the B goes to the A, and Y keep it, and Y keep another Z, control C and D. So it's the same. It just from this to the balance, you can see simply. And the second is, and third actually is this. So this situation. So you can see all the tree goes to right, which is we don't want to see again. This is more or less linked list. So we just rotate the Y on the top again, and X and Z on the left and right, and A, B, and C, D. So here is A, B, and here's the C, D. And the last situation probably is this situation. Here, paste. It's the same situation, but it happens on the right. So now we have all the balanced situations. And then there's one situation is not considered, is empty. Because Haskell asked about the exhausted patterns, because everything is recursive, you can see, and I didn't write the balance for the empty. Just in case, I just write the balance for empty. Well, or not empty. I'm just trying to think. Well, just balance empty for hold on. And another case is probably the not balanced tree. Well, the balanced tree already, and Haskell just asked me to write this as a case, because without adding this, the compiler doesn't tell me is that working. Color left, right equals and here we are. We have implemented all the case of a balancing. So I just adding the instance of tree RBT. Here we are. So the instance of balancing our red tree, as you can see, the first situation is all goes to the left, and second iteration is left, but currently you just keep all y on the top. And third is the all right, and fourth is right and left, but you need to rotate y at the top. Why? Because when you're searching a node on the tree, you first, if smaller, look left, if bigger, look right, but if all bigger, just look all right. Because the tree using the layers, we call it, the first layer, second layer, and third layer, we're using layers to find an element more quickly. Not like array, just or a list, just look like key by key by key. Well, and here we are all the balance. Or let me think if that empty, yeah, empty is a case of balance. And let me think. Yes, we also need to implement the because the red black tree is still a search tree, so we need to implement the binary search tree for the red black tree. So here we are, instant tree BST, instant tree RVT. So I need to implement at least insert t value equals to the so for example, I must define a function for helping inserting the tree, because before the inserting any element, our tree must be balanced. Well, I think I need to delete this. Before inserting things, our tree is balanced or empty. So if I insert a thing to empty, it just goes to middle, which holds the balance situation. But when I insert a thing to the end of the tree, I must trigger the balance to rotate the tree to help to keep the balance. So for example, I define a helper function called INS. So using the guardian, if the value is smaller than x, again, equals balance the tree. Color, keep this the same, and I insert the thing to the left because we already set that. And XR, right. And if otherwise, we go to the second pattern. So we go there and balance the tree, and it should be goes to right. Oh, I forgot the color. I need to add the color, and now seems reasonable. You see, after inserting a element into the tree, first, if inserting the left, I must balance the tree and insert the element to the left. Or insert the right, I must balance the tree first and insert the element to the right. And here's us the helper function, and then the first node defined by red black tree is always black. So I using a black. Let me see. Okay, so here we are. So this function I will define later and call our helping function t, and the call, and here's the helping function where, and it will going to look at the ends function at the end. And the second thing is I probably forgot the non-exhaustive pattern. so I must write the empty. And if the first node implementing the thing, a v, so I will let the first node we created be a red, because that's the definition of the red black tree. Or if you want to reverse, you just write a black. This is your choice, personal choice. And the value and they are empty. And here, more or less, we have all the situation we need to insert to a tree. So here we are. So make black is after rotate, and you will make a black, and then you see this too. First, I make the inserted root be a black root, and then I insert to the tree. And I think here is all the situation we need. Probably we run the GHC for have a look. Let me see. I think you will come. Oh no. So this is 33. No, 96. 96. Or no, I think this is need a capital. Okay, yeah. So we wrote a red black tree. First, we need to check the red black tree. So RBT equals R node. Well, just insert to R empty 1. So you see, the first node is a black node, and then I try to add a second element to that. How about I insert a 1, so I insert a 0. So here the 0 is the left and 1 is on the right. Okay. 3, 2. Let's insert a 2 for going to right. Okay. So now it's a black in the middle. You can see the black is a 1, and left is a red, is a 0, and right is a red, is a 2. So you can see black, red, red. So far, so good. So let's insert in something more, like -1 and -2 for going to the left, and let the 0 be the node. -1. Here goes -2, and you can see RBTT 5. Okay, the node now is a 0 because before it's a 1, and then left have 2 and right only have 1. So you rotate it like this as 0 as a root, and then -2, -1, and here goes 1 and 2. So now we can see the tree balanced. And probably here we are. We have a red black tree. If you want to implement the other function, like these functions, you can implement by yourself because they're the same. And goodbye. And next class, I'm probably going to teach you about the infix trees. for example, Patricia tree or dictionary tree for searching elements on dictionary by. No, I think I need to close.